Okay, so good evening, everyone. I'm Akash Jyoti Pathak. I am a PMRF TA for the NPTEL course, NMR Spectroscopy for Structural Biology. So, so the lecture that was scheduled on Tuesday, last Tuesday, 20th July, so it has been postponed to today, that is 1st August. So I was not able to take the lecture on Tuesday, so I will be taking the live session today. So I'll wait for 1 or 2 minutes and then start today's session. So we are in the week one of the NPTEL course on NMR spectroscopy. So what we will do today is we will start with the basics of NMR spectroscopy. We will learn about the nuclear spin, um, the properties of that arises due to the nuclear spin. So due to the nuclear spin, we get the nuclear spin angular momentum, and we will look into the concept of nuclear magnetic moment, and about the absorption of energies, uh, and what is that which results in resonance, or results in the uh, transfer of spin from one energy state to another. So those concepts we will discuss in detail. So already the concepts have been discussed in the lectures. So I hope all of you have gone through the week one lectures. So we will quickly brush up the concepts, and also we will discuss some important questions related to the week one that will help you in solving the week one assignment. So in the later part of the lecture, we will also discuss in brief about the relaxation, relaxation, and the spin lattice relaxation. And in very brief, I will discuss about the chemical shifts. So the concept of chemical shift will be taken in detail in week two. Uh, so we will also go through some of the questions related to those concepts in week two. But for today, we will just go through the very basics of the nuclear magnetic resonance spectroscopy. So let's start today's session. So I'll start sharing the screen. Okay, so I hope the screen is visible and I'm audible as well. So welcome to this course on to this live session for the course on NMR spectroscopy for structural biology. So minimize this. Yeah, so I'm Akash Jyoti Pathak. I am a PhD scholar in the Department of Biosciences and Bioengineering in IIT Bombay. Um, I am working in a biomolecular NMR spectroscopy lab under the guidance of Professor Ashutosh Kumar. So this course has been taken by, this is a rerun course, and is taken by Professor Ashutosh Kumar and Professor Ramakrishna Husur. So let's start with today's live session. And at any point, if you have any doubt, you can interrupt and ask your question, or you can also use this chat section for posting your questions. So in week one, the lectures that covered the topics on nuclear spin angular momentum. We learned about the nuclear magnetic moment, the spin quantum numbers, what is the absorption energy, or that and in which region of the electromagnetic spectrum can we actually detect the resonance of can we capture the signal of these of NMR, and also we understood about the relaxation. So the two relaxation mechanisms, one is the spin lattice relaxation and spin relaxation, were covered, and we also so this chemical shift concept is dealt in much detail in week two, but there are a few assignment questions related to chemical shift. So what we will do is we will understand this chemical shift concept in very brief in this in today's live session. Um, starting with the first concept about the nuclear spin angular momentum. So so as we all know that matter is made of atoms, right? So and atoms are composed of the electron and nuclei. So the atomic nucleus has four important physical properties. So if we talk about the atomic nucleus, it is composed of the neutrons and the protons. So the atomic nucleus has four important physical properties, and those are mass, electric charge, magnetism, and spin. So the mass of the bulk matter is largely due to the mass of the nuclei, right? A large number of other physical properties such as heat capacity, viscosity are strongly dependent on the nuclear mass. The electric charge of the atomic nuclei is supremely important. Atoms and molecules are bound together by strong electrostatic interactions between the positively charged nuclei and the negatively charged electrons. The chemical properties of each element are determined by the electric charge on the atomic nuclei. So the chemical property will depend on the electric charge, right? The electrostatic interaction between the positive and the negatively charged electrons. But other than the electrostatic property, there are two other properties. One is the nuclear magnetism, and another is the nuclear spin, which are much less evident. But these two properties play a very important role in understanding the in the concept of nuclear magnetic resonance. So the magnetism of a nucleus implies that it interacts with magnetic field like a small bar magnet. So other than this electrostatic interaction and the electric charge of the atomic nuclei, one important property is the nuclear magnetism. And this nuclear magnetism and the atomic nuclei has this property of nuclear magnetism. So this because of this nuclear magnetism, we can consider that the nuclei behaves as a small bar magnet. And because it behaves like a small bar magnet, it can also interact with the external magnetic field. So, however, this nuclear magnetism is very weak and is of little consequence for atomic or molecular structure. The bulk magnetism of some materials, such as iron, is due to electrons, not to the nuclei. So, the magnetism of different nuclei that we talk about, like iron, that is mainly because of the electron, not of the nuclei. But this, but the nuclear magnetism is very weak, and it is not considered in most cases. But the spin of the and even the spin of the nucleus is even so. These two properties, the nuclear magnetism and the nuclear spin, they are less evident, and they are not taken into consideration in most of the cases. But in NMR, when we talk about the concept of NMR, these two properties play a very important role. The spin of a nucleus indicates that the atomic nucleus. So one of the most important concept of NMR is that the nucleus has a spin. Atomic nucleus has a spin, and it is considered that this atomic nucleus is spinning around, like it is rotating in space like a tiny planet. So the nuclear magnetism and nuclear spin have almost no effect on the normal chemical and physical behavior of substances. So the chemical and physical behavior of substances uh, are determined or are influenced by these properties, by these physical properties like mass, electric charge, right? But the other two properties, that is the nuclear spin and magnetism, nuclear magnetism, it is a wonderful tool for spying on the microscopic and internal structure of the objects without disturbing them. Okay, so yeah, so what is the nuclei is basically has two important properties which is utilized in NMR. One is the nuclear spin and another is the nuclear magnetism. Okay. Nuclear magnetism. So because of this nuclear spin, it has a spin angular momentum, which we will discuss in the next slide. Okay, spin angular momentum. So anything in as we know or as we have already learned in classical physics, that any object that is spinning will have an angular momentum, is associated with the spin angular momentum. So because the nuclei has a spin, the spin or the angular momentum that is associated with the nuclear spin is called as nuclear spin angular momentum. And because of the nuclear also has a is also behaves as a because so what happens is anything that is spinning will also result in the formation of a magnetic field around it. Okay, so the nuclear also has a nuclear magnetism, which gives to the property of nuclear magnetic moment, which we will discuss. These two things we will discuss in the upcoming slide. So because of this magnetic property of the nuclei, it can interact with magnetic field, and these magnetic fields may come from the molecular environment. Example, the surrounding electrons or from other nuclear spins in the same molecule. Magnetic fields may also originate from sources outside the sample, such as the external apparatus. So we will discuss these things in detail. So first, coming to the spin. So nuclear spin is a highly abstract concept, and for understanding the spin, a lot of quantum uh, mechanics principle has to be considered, but those concepts are beyond the scope of this course. So we will understand in a very simple manner what is when we talk about nuclear spin, what uh, what can we understand in a physical manner. Okay. So the spin is a highly abstract concept. So, so as I was explaining, that any rotating object possesses a quantity called angular momentum, right? We all have known that angular momentum is denoted by this symbol omega. So anything that is spinning will have a angular momentum. Okay. So now this angular momentum is a vector quantity, and we can get the direction. So because it is a vector quantity, it will have both a magnitude and a direction. And the direction of this spin angular momentum, or the direction of this angular momentum, can be obtained by using the right hand thumb rule. So for example, if your molecule is rotating in the anti-clockwise direction, then the your fingers, you will curl your fingers in the anti-clockwise direction, and the direction of the thumb will point to the, or the direction of the thumb will indicate the direction of the spin angular momentum. Okay. Okay, so as you can see in this figure, so if your spin is in the anti-clockwise direction, then your thumb will point towards the, or your thumb will indicate the direction of the spin angular momentum. Okay, so your so that is what is written over here. So your right hand may be used to figure out which way the arrow points. If your thumb points along the rotation axis, then the right hand fingers wrap around in the direction of the rotation. So your fingers, your right hand fingers will curl in the direction of the rotation, and your thumb will provide the direction of the angular momentum. Okay, I hope this is clear. So moving to the next slide. So now coming to quantum angular momentum. So because this nuclei has a spin, has a is associated nuclei has a nuclear spin, so it will also have its it will also have an angular momentum. So in quantum mechanics, angular momentum is quantized. What do you mean by quantized? So angular momentum is quantized. It means that it can take only certain values, certain discrete values. It cannot take any values. So it will take certain discrete values. So the component of spin angular momentum along any axis is always either h by 2 pi, or so this is actually h bar by 2, or so h bar is basically h by 2 pi. So it is always either plus h bar by 2 or minus h bar by 2, where h bar is equal to h by 2 pi, and this is the reduced Planck's constant. Hence, these particles are said to be spin half particles. So basically, what is happening over here is that so we will talk about the spin quantum number. So if a nuclei has a spin quantum number of half, then it can have so the component of the spin angular momentum can have two values. It will be either h bar by 2 plus h bar by 2, or it will be minus h bar by 2. So we will look at these two things in detail in the upcoming slide. But for now, just understand that because this nuclei has a spin, it will also be associated with a nuclear angular momentum. Okay. So for the nuclei which is having a spin quantum number of half, or which is having a spin half, the angular momentum will have two values. One is h bar by 2, or it will have minus h bar by 2. The spin quantum number of the ground state, referred to as its intrinsic nuclear spin, is represented by the letter I. So the spin quantum number is denoted by the letter I. The corresponding spin angular momentum is represented by the vector I, and has a magnitude given by h bar root over I plus 1. So every nuclei, all the nuclei which is present, which are NMR active, can be denoted by the letter I. Okay. So spin quantum number, I is what? I is the spin quantum number of a particular nuclei. Now, how is the spin quantum number related to the angular momentum of a nuclei? So the quantum angular momentum can be actually denoted by the letter P. Okay, and this value, this P magnitude. So angular momentum is also a vector quantity. Okay, so the magnitude of the spin angular momentum, magnitude of the spin angular momentum is represented, or it is given by the expression h bar root over I plus 1. Okay. So if you know the spin quantum number of a nuclei, then you can determine its angular momentum, spin angular momentum, by this expression. So for a nuclei which is having a spin quantum number of half, its angular momentum will be half into half plus 1, root over half into half plus 1, which will be, just give me a moment. Okay. Yeah. So as the nucleus has a spin, so it is also associated with a spin angular momentum. And this spin angular momentum, we saw that it has a direction. It is a vector quantity. It is having a direction. The direction is provided by the right hand thumb rule. where the direction of the thumb indicates or provides the direction of the spin angular momentum, and the magnitude is given by this expression, which is h by root I plus 1. Now, what is the quantum number of a nuclei? So, the spin quantum number of a nuclei, so it can have either it can have values like 0, or it can have half integer values, or it can be a integer value. So the if the atomic nuclei has an atomic number which is even, and if the isotope number is also even, okay, so the mass number and the atomic number, if both are even, then the spin quantum number is 0. Okay, if the nucleus has an odd mass number and a yeah, so if it is an odd mass number, then it can take spin quantum numbers half, 3 by 2, 5 by 2, and so on. So for example of such nuclei are N15, 7, then you have carbon 13, 6. So all these nuclei, or you can also have P31, right, 15. So all these nuclei, if you see the mass number of these nuclei, they are having a odd atomic mass number. So if a nuclei has odd atomic mass number, then it can take half integer values. Okay, half integer values. While if the nuclear spin takes integer values like a nuclei can also take integer values like 1, 2, 3, and which type of nuclei will take such values? So for nuclei which are having odd atomic number and even mass number. Okay, odd atomic number and even mass number is example is like deuterium. If you see, it is having an odd atomic number and even mass number, right? 1:2. So it is an isotope of hydrogen. So these type of nuclei which are having odd atomic number and even mass number will take spin quantum number equal to integral spin quantum numbers like 1, 2, 3, and so on. Okay, so there are three cases. So a nuclei can have 0 spin quantum number. So those type of nuclei are NMR inactive. So if the spin quantum number I for a nuclei is 0, then it is NMR inactive. While if nuclei have integer values or half integer values, then such type of nuclei are NMR active. So a nuclei can, what are the three conditions that we discussed? So first is that a nuclei can have odd atomic number, and even mass number. So in that case, it will take integer values 1, 2, 3, and so on, even mass number. If the both the atomic mass number and the if both the mass number and the atomic number both are even, then it will have a spin quantum number I equal to, so what is this? It will have 1, 2, 3. If it is even, so for even number, it will have spin quantum number 0. So if the atomic number and mass number both are even, then it will take spin quantum number 0. And the third case is that if the atomic mass number is odd, then the spin quantum number will be half integer values. So it can have values like half, 3 by 2, 5 by 2. So common examples are nitrogen, carbon, phosphorus, and proton, right? One of the most discussed nuclei for NMR spectroscopy is the proton or the hydrogen uh, nuclei, right? So, so now coming to spin angular momentum. So the nuclei, because it has a spin, it is associated with the spin angular momentum I. This is an intrinsic property. Now, what happens is, because of the spin angular momentum, it gives another intrinsic property to the nuclei, which is called the magnetic moment. So magnetic moment is denoted by the magnetic moment quantum number mu. So mu is also a vector quantity, which is represented by the symbol mu, and the magnetic moment and spin angular momentum of a nucleus are linearly related. Okay, so basically, so if you denote the spin angular quantum or the spin angular momentum, if you denote the spin angular momentum by the letter I, so there are different notations. So in different books, you will find that they have been denoted by different same letters. So if you denote the spin angular momentum by the letter I, then the spin angular momentum is directly proportional to the magnetic moment mu. Okay, so the magnetic moment, so any spinning object will produce a magnetic field around itself. So uh, this is denoted by the this is called the magnetic moment, nuclear magnetic moment, which is denoted by the letter mu and Greek letter mu, and it is also a vector quantity. So both spin angular momentum and magnetic moment both are vector quantities. Now, when you remove this proportionality, you get a constant which is called gamma. So I is equal to gamma mu. So this gamma, this constant is called the gyromagnetic ratio. So gyromagnetic ratio is the ratio of the spin angular momentum and the magnetic moment. Okay. So the result, what we looked, so what have we discussed so far is that the nuclei has two intrinsic property. One is the spin, and another is the magnetic moment. So spin is indicated by the letter I, and magnetic moment is denoted by the letter mu, and they are directly proportional to each other. So when you remove this proportionality, you get a constant which is denoted by the symbol gamma. So gamma is called the gyromagnetic ratio or the magnetogyric ratio, which is a characteristic of the given nucleus. So every nucleus has a characteristic gyromagnetic ratio value. This constant, this value can be, or this ratio, this constant can have a positive value or it can have a negative value. So some nuclei have positive gamma and some others have negative gamma. Okay, so depending upon this sign, the magnetic moment and the angular momentum vectors are oriented in the same direction or in opposite direction. So what happens? So because this spin angular momentum is equal to gamma mu, so if your gyromagnetic ratio takes a negative value, if your gyromagnetic ratio takes a negative value, then what will happen? Then it will, so both of these are vector quantities, right? Spin angular momentum and magnetic moment, they are spin angular momentum and magnetic moment, they are both vector quantities. So if this gamma is having a negative value, then the spin angular momentum and the magnetic moment will be opposite to each other, right? While if if this value is positive, then they will be in the same direction. They will be in the same direction or they will be in opposite direction. So yeah, so as I was discussing that this is an intrinsic property of the nucleus. So every nuclei has its own gyromagnetic ratio. So for proton, it is 267.522 radian per second per Tesla into 10 to the power 6. Okay, for deuterium. So proton it is 267, for deuterium it is 41, for carbon 13 it is 67. So one important relation to remember or note over here is that the proton and carbon has a gyromagnetic ratio which differs by a factor of 4, right? So if you so the gyromagnetic ratio of carbon 13 is 4 times lesser than the gyromagnetic ratio of the proton. Okay. So if you like divide 267 by 67, then approximately you will get a value of 4. Okay. So this relation is useful in solving certain problems. So these values will not always be mentioned in the question, but there can be questions that would ask you to calculate the frequency of given the given the magnetic field. You might be required to calculate the frequency of carbon 13. So if you know the relation of these two, how the gyromagnetic ratio of these two nuclei are related, then you can directly calculate it. So we will go through some of the questions in the later lecture. So, but for now, just remember that they are differs by a factor of 4. Okay, 15N is having a negative gyromagnetic ratio value. So this is important. So there might be some questions like which nuclei has a negative gyromagnetic ratio. So remember that nitrogen 15 has a negative gyromagnetic ratio. Then another NMR active nuclei is F19 and P31. Um, so if you see here as well, so those nuclei which are having a mass number odd, which are having an odd mass number like H1, 13C, 15N, 19F, 31P, they all are having nuclear spin quantum numbers half, half integers. They are having half integer values, while those nuclei which are having a even mass number will have integer values like 1, 2, 3. So here also you can see the values. So 14N and each 2 is they are both having even mass number. So as a result, they are having integer values. So these are the natural abundance. So why both these all these three properties are very important properties which make a nuclei NMR active. So the greater the natural abundance and the higher the magnetic ratio, the will such nuclei will have better absorbance values. Okay, the signals of such nuclei will be we will get very sharp peaks for such type of nuclei. Okay, now coming to the spin quantum number. So any atomic nuclei that possess. Okay, so now coming to spin quantum numbers. So the spin quantum number, as we discussed just now, that it can have values 0, it can have half integer values, or it can have integer values. Okay, so the spin quantum number is it can be determined from the atomic number and the mass number. So depending on whether your mass number is odd or even, you can comment on what value will be taken up by the nuclei. Okay, so any atomic nucleus that possesses either odd mass number or odd atomic number or both. So nuclei can have a odd mass number, odd atomic number, or both, has a quantized spin angular momentum and a magnetic moment. So the more common nuclei that possess spin include the proton, this deuterium, 13 carbon, 14N, 17O, 19F. Notice that nuclei of the ordinary isotopes of carbon and oxygen. So the ordinary isotope of carbon and oxygen are what they are 12C. 12C, right? Carbon 12 is the uh, is the most abundant isotope of carbon, and 16 oxygen, O16 is the most abundant isotope of oxygen, right? So they are not included among those with the spin property. So here if you see that the atomic number is even and the mass number is also even, so both these nuclei have spin quantum number 0. Okay, I equal to 0. For each nucleus with spin, the number of allowed spin state it may adopt is quantized and is determined by its nuclear spin quantum number I. We have been so what we are saying that the angular momentum is quantized. So what will be the values? How many values can a spin angular momentum take? So that will be the spin angular momentum can take values from plus I to minus I, and there are 2I plus 1 allowed spin states. Okay. Is this point clear? So for each nucleus with spin, the number of allowed spin state it may adopt is quantized and is determined by the nuclear spin quantum number I. So for each nucleus, the number I is a physical constant, and there are 2I plus 1 allowed spin state with integers differences ranging from plus I to minus I. So if we consider the example of proton, so it is having a spin quantum number of half. right? So the spin quantum number, that is I is half. So it will take values from minus half to plus half. And how many total values it will have? So it will have values 2 into half plus 1. That will, what are those two values? Minus half and plus half. Okay, minus a half and plus half. So it will have values ranging from plus I to minus 1. So for example, if your spin quantum number of a nucleus is 3 by 2, then it will have values ranging from minus 3 by 2 minus I to plus I, minus 3 by 2 to plus 3 by 2. And each of these quantum spin quantum states will differ by. So how many total values it will have? It will have 2I plus 1 values. Okay, 2I plus 1 values. So you substitute the value of the spin quantum number 3 by 2, and then you will get, so you will have 4 different values. So what will be these 4 different values? So it will be minus 3 by 2, then minus 3 by 2 plus 1. So what is minus 3 by 2 plus 1? It is minus half. Then again you do minus half plus 1. Minus half plus 1 will be what? You do minus half plus 1, then you will have half. Then again you add 1 to the previous previous spin quantum value. Then you will be having half plus 1 is 3 by 2. So it will have 4 different values, which will be minus 3 by 2, minus half, half, and 3 by 2. Okay. So in the absence of an applied magnetic, so this is another important point. So in the absence of the applied magnetic, so when you are not applying any external magnetic field, all the spin states of a given nucleus are of equivalent energy. So all these 4 different spin states, all these 4 different spin states are degenerate. What does degenerate mean? That all these spin states are having the same energy. All of the spin states should be almost equally populated with the same number of atoms having each of the allowed spin. So here some of the spin quantum numbers of the common nuclei have been given. For proton it is half, for deuterium it is 1. So all the even atomic mass number nuclei, C12, 14, 16, oxygen O16, they are having 0 quantum spin quantum numbers. 13C will have half. Uh, 5 by 2, so oxygen, so remember these. So how do you get these values? They are obtained from very complex quantum calculations, which is beyond the scope. So you have to remember the spin quantum number of some of the nuclei. So for proton, C13, N14, you can easily remember. But for these two nuclei, remember that O17 has a spin quantum number of 5 by 2 and chlorine has a spin quantum number 3 by 2. So the number of spin states, how will you get the number of spin states? So you will use the formula 2I plus 1. 2I plus 1. So you substitute the value of the spin quantum number in this equation and you will get the number of spin states. So this one will have 2 spin states. This deuterium will have 3 spin states. C13 will have 2 spin states, and accordingly you can get the values of the number of spin states. Okay. Now coming to the nuclear magnetic moment. So spin states are not of equal energy in an applied magnetic field. So when you apply an external, so before you are applying any external magnetic field, all the nuclear spins will be degenerate. They will possess the same energy. Now, once you apply the external magnetic field V naught, then there will be then you will these nuclear spin will get can attain different states. Okay, depending on the I value. Okay. So that is what. So spin states are not of equivalent energy in an applied magnetic field. So these states that we talked about in the previous slide, like proton, a proton nuclei can have 2 states. Now these 2 states are not having the same energy. Similarly, if we talk about chlorine has 4 spin states. Now these 4 spin states are not of equivalent energy in presence of an external magnetic field. So they are not of equivalent energy because the nucleus. Now another thing is that because the nucleus is a charged particle and any moving charge generates a magnetic field of its own. Okay, so any moving charge will generate a magnetic field of its own. So this magnetic field that is generated by a nuclear spinning, due to the nuclear spinning about its axis, is given by the term nuclear magnetic moment and denoted by the Greek letter mu. So this nucleus has a magnetic moment m. Some in some books you will see that it is denoted by denoted by the letter m, and it is generated by charge and spin. Okay. So a hydrogen nucleus may have a clockwise or magnetic moment in two cases are pointed in opposite direction. So if it is having, so just now we saw that it can have two values, right? The spin angular momentum can have two values. That is, it can have a plus half value and a minus half value. So the plus half value will point in one direction. The magnetic momentum will point in one direction, and the negative value will point in the opposite direction. Okay, it will point in the opposite direction. So in an applied magnetic field, all protons have their magnetic moments either aligned with the field or opposed to the field. So as I was talking that this proton can have two values, plus half and minus half. So plus half would indicate that it is oriented in the same direction as the magnetic field. So it is having a spin half, and the spin state which is having a value minus half, it is its magnetic moment. Its magnetic moment will be opposite to the the direction of the external magnetic field. Hydrogen nuclei can adopt only one or other of these orientation with respect to the applied field. So it can take either a plus half spin state, or it can have a minus half spin state. So remember that this plus half, we will talk about the energy. How do you quantify the energy associated with each spin state? Okay, so energy, what is the energy associated with each spin state, we'll be discussing in the next slide. But for proton, it can take the spin state plus half and minus half. And remember that this plus half state is having a higher energy than the sorry, plus half state is having a is having a lower energy than the minus half state. Okay. So when we derive the expression of energy of a particular spin state, then you will understand that why the plus half spin state has a lower energy than the spin state or minus half. Okay. So yeah, coming to the concept of energy. So what are the so till now what all did we learn? So we learned that the nuclei has a spin, a spin. So which is a very abstract term, and we require certain quantum mechanic model to understand what is meant by a nuclear spin model. But in a physical sense, if we talk about the nuclear spin, then we say that every nuclei, NMR active nuclei, has a nuclear spin, and because of this nuclear spin, it has its own spin angular momentum. Now, this spin angular momentum is a vector quantity, and because it is a vector quantity, it will have both a direction and a magnitude. So, the direction of the spin angular momentum can be obtained by the right hand thumb rule. So, the direction of the thumb. So, if you your fingers will point to the direction of the spin, and the your thumb will point to the direction of the thumb will give the direction of the spin angular momentum. And we also learned about the expression of spin angular momentum. So the spin angular momentum is given by this expression h bar root over I into I plus 1. Okay. Then we also discussed about the spin quantum number I. So we discussed that we learned that the nuclei which have atomic mass number odd uh, or uh, the atomic number odd, they will have either integer values or half integer values. While for those nuclei which are having both atomic mass number even and atomic number even, they will have spin quantum number 0. So nuclei which have spin quantum number 0 are NMR inactive. Okay. Next, we saw that because a nuclei has a spin of its own, and any spinning object will generate a magnetic field around itself. Okay, so this magnetic field which is generated by a spinning nuclei is denoted or is defined by the by a term which is called as the nuclear magnetic moment. Okay, nuclear magnetic moment M, and or in some cases it is also denoted by the letter mu. Okay, and we also saw that the spin angular momentum and the magnetic moment is directly proportional to each other. Right. So the spin angular moment, if it is actually here, it is a bit confusing. So just consider remember that spin angular momentum is denoted by the letter p, while the spin quantum number is denoted by the letter I, and the spin angular momentum is directly proportional to the magnetic moment mu, is directly proportional to the magnetic moment of the nuclei. So when we remove this proportionality constant, we get a constant term which is called as gyromagnetic ratio. So the spin angular momentum p is equal to gamma I, or sorry, is equal to gamma mu. Okay, gamma mu. Or what we can say that the angle, yeah, this nuclear magnetic moment is equal to gamma p. So the nuclear magnetic moment is directly proportional to the spin angular momentum. Directly proportional to the spin angular momentum, and which is the which is related to each other by this gyromagnetic ratio gamma. So now we also learned that in presence of an external magnetic field, this spin will acquire different spin states. So it can have spin states from minus I to plus I, and how many spin states will be there? It will have 2I plus 1 spin, 2I plus 1 spin states. Okay. Now we will look at the what we, here in this slide we will talk about what is the energy associated with each of the spin state. So the nuclear magnetic resonance phenomena occurs when nuclei aligned with an applied field are induced to absorb energy and change their spin orientation with respect to the applied field. So you can see over here. So this is the ground state of the nuclei. Now you have applied an energy h nu. So when you have applied this energy h nu, the energy will be absorbed by the nuclear spin, and it will transition from one energy state to the other energy state, to a higher energy state. So I have applied this energy h nu, and now the nuclear spin has moved from a lower energy state to a higher energy state. Okay, so always remember that the plus half is the lower energy state and minus half is the higher energy state when we are talking about proton nuclei. Okay, so the energy absorption is a quantized process, and the energy absorbed must be equal to the difference between the two states involved. So quantized means that it can take only certain values, and what the delta E. So it can only move from one state to another state if you are applying an energy which is equal to the energy difference between the two spin states. So this is given by h nu. So in case of proton, then the absorbed energy for transitioning a nuclei from a lower energy state to a higher energy state will be given by this expression E minus half state minus E plus half state. So delta E. So this is basically delta E is equal to h nu. So energy difference is a function of the strength of the applied magnetic field B naught. Uh, so uh, so what you can see over in this figure, here in this figure, that when no magnetic field is applied, all the spin states are degenerate. They are having the same energy. Now, when you are applying an external magnetic field, they we get two different spin state. One is the lowered energy state, which is called the plus half, and the another is the minus half, which is against the field. So this mu here is against the against the field means what? Here is the nuclear magnetic moment is opposite to the externally applied magnetic field. So if your magnetic field is in this direction, upward direction, then your magnetic moment will be in the direction in the downward direction, minus half. Okay, so the spin states of a proton. So this is basically showing the figure is showing the spin states of a proton in the absence and in the presence of an applied magnetic field. Okay, now the energy of this state is directly proportional to the external magnetic field that is applied. Okay, so we will derive this expression now. So you can see here that for a nuclei which is having a spin quantum number of 3 by 2, it can take values from minus 3 by 2 to plus 3 by 2 And how many values it will have? It will have 2 into 3 by 2 plus 1. So it will have four different spin states. So as a result, for chlorine, you can see chlorine has a spin quantum number of 3 by 2. So it has four different spin state: minus 3 by 2, minus half, half, 3 by 2. Okay. So what are the direction? What are the direction of these spin angular momentum? So these plus 3 by 2 and minus 3 by 2 will take this direction, and plus half and minus half will be having this direction. Okay. So I hope the recording. Okay. So yeah, so this is what I was saying, that the energy difference between the two states is directly proportional to the external magnetic field. So the stronger the applied magnetic field, the greater the energy difference between the possible spin states. So this energy difference is directly proportional to the external magnetic field, or the applied magnetic field. So now when you remove this proportionality, then you get a constant which is denoted by this letter F. Now, other than this magnetic field, applied magnetic field, it also depends on the particular nucleus. So what is the nucleus? Whether it is proton, whether it is 15 and nitrogen 15, whether it is carbon 13, that also determines that what will be the energy separation between the two states. So each nucleus, hydrogen, chlorine, and so on, has a different gyromagnetic ratio. Uh, so, uh, so gamma is a constant for each nucleus and determines the energy dependence on the magnetic field. So we saw that the energy difference is dependent on the magnetic field, applied magnetic field, and it is also dependent on the gyromagnetic ratio. It is also dependent on the nuclei which you are considering over here. Nuclear is again the gyromagnetic ratio will determine that what is that particular nucleus, right? That each nucleus will have a particular gyromagnetic ratio. So this energy difference is actually equal to the gyromagnetic ratio and the applied magnetic field. So now what happens is since this angular momentum of the nucleus is quantized, so it is quantized in you. So this all we know in class. We have been learning in since class 11, isn't it? So the angular momentum, if anything is quantized, then it will be having the units of h by 2 pi. So what happens? The final equation that we get, that this energy separation between the two states is given by the equation gamma h by 2 pi b naught. Okay, so what did we learn from this slide is that the energy difference between the two states is dependent on the applied magnetic field, and it is also dependent on the type of nucleus, which means that it is dependent on the gyromagnetic ratio of the nucleus. So when you remove this proportionality constant, what you get h by 2 pi gamma b naught. Okay, so so basically delta E equal to h nu, right? So you can, this entire term is basically your frequency. So your frequency, what is your frequency? From here you can say that your frequency is gamma b naught by 2 pi. So this is basically the resonance frequency. So if you have two exciter a nuclear spin state from one energy state to another energy state, then you have to apply an energy which is equal to the this value, this h nu value. So and nu will be equal to the gyromagnetic ratio of the nuclei, v naught and the 2 pi. So this is a very important expression. Okay, when we are discussing about NMR spectroscopy, this is a very important expression. So delta E is basically the separation between the two spin state, and that is given by this expression delta E equal to h by 2 pi gamma b naught. Okay. And your resonance frequency is what? Your resonance frequency is gamma b naught by 2 pi. Gamma b naught by 2 pi. So your resonance frequency is directly proportional to the gyromagnetic ratio of the nuclei and the applied magnetic field. Okay, so remember this expression, because towards the end we will solve a few questions where you will be required to apply these equation for solving the question. So I hope you have understood. If you have understood, then you do not have to memorize anything. Just understand the concept, and it will be quite the course will not be very difficult for you to understand all the concepts. So if the correct value for the proton is substituted, one finds that an unshielded proton should absorb radiation of frequency 42.6 megahertz in a field of strength 1 Tesla, or radiation of frequency 60 megahertz in a field of strength 1.4 Tesla. Okay, so basically for proton, so it is having delta E equal to, just now we derived the expression what it is H gamma B naught by 2 pi. So if you substitute the values, if you plug in the values of gyromagnetic ratio of proton, the magnetic field you are substituting here 1 Tesla. You are considering here that 1 Tesla is the externally applied magnetic field, and you put in the values of pi 3.14 and put in the values of Planck's constant 6.296 into 10 to the power minus 34. Then accordingly you will get the energy difference. The energy difference will come out to be 42.6 megahertz. Okay, 42.6 megahertz. So if the field if it is present in a magnetic field of strength 1 Tesla, or if you keep it in a field of strength 1.41 Tesla, then you will get a frequency of 60 megahertz. So here in this table you can see that in different magnetic fields have been calculated in this table. So remember that 1 Tesla is equal to 10,000 Gauss. Okay. Sometimes these conversion factors are necessary, uh, come in handy. And you can see here, just give me a moment. Okay, you can calculate the energy difference between the two states from this equation. So for a proton, the nucleus of a hydrogen atom, if the applied magnetic field has a strength of approximately 1.41 Tesla, the difference in energy between the two spin states of the proton is about 2.39 into 10 to the power minus 5. It is 10 to the minus 5 kilojoule per mole. So radiation with a frequency of about 600 of about 60 megahertz will lie in the radio frequency region of the electromagnetic spectrum corresponding to this energy difference. Okay, so now what happens now? Another concept comes here is that when the magnetic field is applied, external magnetic field is applied, the nucleus begins to precess about its own axis of spin with angular frequency, which is called its Larmor frequency. Okay, so what we saw just now is that when we are applying an external magnetic field, the nuclear spin state is getting degenerate. or it was degenerate, now it is having different energies. It will be split into different energy state. Uh, so uh, so this is the difference between the energy states or the spin states. You can call them as energy state. So now along with this difference in along with this do with the nuclei having two different energy state, it will also uh, precise. What happens is that it will also precise about the about the externally applied magnetic field. Okay, which is called the Larmor frequency. So this is basically the you can see in this figure. So it will also start rotating about the z axis. So this the spin about this z axis is called the Larmor frequency or omega. Um, and so you can hear what has been shown in this figure here. An example of a spinning top has been given as an analogy. So when you spin a top, so it also it is rotating about its own axis, but along with it, when it if you when the motion of the spinning top is about to stop, you can observe that it also starts rotating about the gravitational field, externally applied gravitational field. So it will also start rotating about a particular axis. So that is the case. As a similar analogy can be considered when we are talking about the nuclear spin. So it is rotating about its own axis, but along with it, it is also rotating about the external magnetic field, or it is if the direction of the externally applied magnetic field is considered in the z direction, then it is also precessing, or it is also rotating about this z axis or the externally applied magnetic field. So the frequency at which a proton precesses is directly proportional to the strength of the applied magnetic field. The stronger the applied field, the higher the rate of precision. So for a proton, so this will again also, so this Larmor frequency is also dependent on the external magnetic field V naught. Okay, and the higher the magnetic field, the more will be the Larmor frequency, or the rate of precision will be higher. So for a proton, if the applied field is 1.41 Tesla, the frequency of precision is approximately 60 megahertz. Okay. Now coming to what is resonance in NMR nuclear magnetic resonance? What is resonance? So now, so we already have understood, but just to summarize everything, let's understand this slide once again. So the nuclear magnetic resonance process will only occur when you provide a frequency which is equal to the Larmor frequency of the nuclei. Okay, so when nu will be equal to omega, omega is the Larmor frequency, then only the nuclei will absorb that particular energy and it will transition to a higher energy state. Okay, so what is let's understand one by one what is happening. So since the nucleus has a charge, this precision generates an oscillating electric field of the same frequency. Okay, if the radio frequency waves of this frequency are supplied to the precessing proton, the energy can be absorbed. So it is having a particular energy, right? It is having having a particular Larmor frequency. So if it is having a particular Larmor frequency, it is also associated with a particular energy. Now this energy, when this energy will be equal to the energy which is applied, then you can see that the resonance will take place. Okay, so that is when the frequency of the oscillating electric field. So because this is a charged particle, it will generate an electric field around itself. So this oscillating electric field component will have a particular energy, and when the frequency of this oscillating electric field component of the incoming radiation just matches the frequency of the electric field generated by the precessing nucleus, the two fields can couple and the energy can be transferred from the incoming radiation to the nucleus, thus causing a spin change. Okay, so from plus half, it will move to minus half. Okay, your minus half is the higher energy state. Minus half is the higher energy state. Actually, one more thing to note over here is delta E is equal to minus gamma H nu. Okay, minus gamma H nu. So that is why if your magnetic moment is negative, if your magnetic moment is negative, then your delta E will be positive. And if your magnetic moment is, or if your spin angular momentum, your spin angular spin quantum number, if it is if it is positive, then it will have a, so basically what is happening is that delta E is equal to minus gamma B naught by 2 pi. Okay. So now if you again substitute this value, so you we already discussed that mu is equal to gamma P. Okay, mu is equal to gamma P. So now P is what? P is again your H bar I, H bar root over I into I plus 1. Okay. So basically what will happen here is that if your I is equal to minus half, okay, then this delta E will be what? Minus multiplied by minus will give you a positive term. Okay, so positive energy, but if your I is half, if it is positive half, then your delta E will be what? It will be negative. So negative energy means it is more stable, and positive energy, positive, if your delta energy difference is if your E comes out to be positive, then it will be having a higher energy state. Okay, so that is why your minus half is always the higher energy state, and your plus half is the lower energy state. Plus half spin state will have a lower energy compared to your minus half. Okay, I hope this thing is clear. Gamma B naught H by 2 pi. Okay, and one more thing is that what we have learned from the previous lecture is that mu is equal to gamma P. Okay, so basically you can get here I into I plus 1, you will get over here B naught. So if your I is equal to minus half, then your E will be positive, and if your I is equal to plus half, then your E will be negative. So this plus half is having a lower energy state, and your minus half will have a higher energy state. Minus half will have a higher energy state. Okay, now let's quickly understand this. So when you apply a frequency, incoming radiation, or the incoming radiation, if it has a frequency which is equal to the Larmor frequency of the nucleus, then the resonance will take place. So that is all that you have to understand. Now, the population densities of the nuclear spin state, which means that initially when no external magnetic fields are applied, external magnetic field is applied, all the spins will have the same energy. Now, in presence of an external magnetic field, there will be, you will get two spin states for proton. Now, these two spin state will have different energy, right? They will have different energies, and uh, now the population of the nuclei in the higher energy state and the population of nuclei in the lower energy state can be given by this Boltzmann distribution equation, n upper by n lower. So n upper is the number of nuclei in the higher energy state, and n lower is the number of nuclei in the lower energy state. So this is given by this Boltzmann distribution equation. So n upper by n lower is equal to e to the power minus delta E by kT. K is the Boltzmann constant, delta is the energy difference between the two energy states. So this is delta E. So if you plug in all these values, so if you put the Planck's constant 6.624 into 10 to the power minus 34 joule second, Boltzmann constant 1.38 into 10 to the power minus 23, and T is the absolute temperature, then you can calculate the population difference between the two energy states. So the energy difference between the upper and the lower energy state, delta E. Delta is the energy difference. Since using delta equal to each nu, the second form of equation is derived. Nu is the operating frequency of the, yeah, here nu is basically the operating frequency of the instrument, and each is the Planck's constant. So if you put the temperature, absolute temperature, if you put it at absolute temperature means temperature in Kelvin. If you consider it as 25 degrees Celsius or 298 Kelvin, then what you will get from this equation, you will get that the number of nuclei which is present in the upper energy state is, there are 9 more nuclei which are present in the upper energy state compared to the lower energy state. Okay, so you will get a factor of this 1 into 10 to the power 6 divided by is 100,009. So the lower energy state has 9 nuclei in excess compared to the upper energy state. Okay, so in approximately 2 million nuclei, there are only 9 more nuclei in the lower spin state. Okay, lower spin state is the lower energy state, so there will be more number of nuclei, but this difference is only of, the difference is only of 9 when you are applying a frequency of 60 megahertz. So as you are increasing the frequency from 20 to 600, you can see that the number of excess nuclei are increasing, is increasing. Okay, so there, so if you are applying a frequency of 600 megahertz, then there will be the population difference between the two energy state will be 96. Okay, so if we increase the operating frequency of the NMR instrument, so you will see that there are different type of NMR spectrometers. So always for a good signal, we always what we try to use, we want to use uh, higher megahertz spectrometers, right? 750, 800, 850 megahertz. So the better the operational frequency of the NMR instrument, the better peak resolution we will get. NMR peaks will be obtained. So if we increase the operating frequency of the NMR instrument, the energy difference between the two state increases, which causes an increase in this excess. Okay, so it is this difference. So this difference in this population is what is detected. Okay, so that is what is when the 60 megahertz radiation is applied, it not only induces transition upward but also stimulates transition downward. This is also an important point. If the population of the upper and lower states become exactly equal, we observe no net signal. This situation is called saturation. So if you apply a very high energy of radio wave frequency, then at one point what will happen, a saturation state will be achieved. So you would not want saturation. So if there is if the number of nuclei in the upper state and the number of nuclei in the lower state becomes equal, uh, then there will be no signal. So you will not want to have a saturation situation. Okay, so you have to control the energy of the radio wave frequency. I hope this point is clear. So how do you get this the population difference? So basically that is what is explained here. The thermal energy resulting from room temperature is sufficient to populate both of these energy levels, since the energy separation between the two levels is very small. So it is 2.39 into 10 to the power minus 5 kilojoule per mole when the external magnetic field is having the external frequencies of 60 megahertz. So because this difference is very low, it can the thermal energy or in the room at room temperature condition will be sufficient to uh, get a population will end on the lower energy state. Okay. Now, few concepts we will discuss before we discuss about the spin relaxation and the spin lattice relaxation. They have already been covered in the lecture. We will quickly brush up what has been already discussed in the lectures. So, one is the bulk magnetization. So what is bulk magnetization? Is basically just now defined that all the nuclei will have a particular nuclear magnetic moment. Okay, nuclear magnetic moment, and each of these nuclear magnetic moment, they are oriented in different directions. Now, because they are all the nuclei is associated, they are spinning. They will have their own. They will produce a local magnetic field. Each nuclei will produce a local magnetic field. Now, when you sum up all these local magnetic fields, so this magnetic field will again will have components in the XY direction and components in the Z direction. So because they are randomly oriented, what happens is the components in the XY direction, they cancel out each other. And what you are left with is the components in the Z direction. So when you sum up all the components in the Z direction, sum up all the these local small magnetic fields in the Z direction, then what the term that you get is called the bulk magnetization. So this bulk magnetization is having a net direction in the is having a resultant direction in the Z axis. Okay, so that is what is explained. Some nuclear appear to contain a source of spin angular momentum, right? Yeah. So as we discussed, that there are few nuclei. If we look at the periodic table, then all those nuclei which are having odd atomic mass number or odd atomic number or both, they will be having a particular spin quantum number, and because they will have a spin quantum number, they will associate with this particular spin angular momentum, right? So the spin angular momentum, that it turns out that associated with the spin angular momentum, there is always a nuclear spin magnetic moment. Okay, so that is what we saw, that this spin angular momentum, that is mu magnetic moment, is directly proportional to P or directly proportional to I. Okay, so it is all spin are associated with a magnetic moment. So what this means is that the nucleus generates a small magnetic field just as if it were a tiny bar magnet. Okay, so you can consider the different nuclei. So, for example, if you have this molecule CH2, CH2, CH3, then all these protons that are there in this molecule, they will all have a particular, each of this proton will behave as a tiny bar magnet. Each of them will have a will have a small magnetic field. Okay, so when the nucleus is placed in the magnetic field, there is an interaction between the nuclear moment and the applied field. So your applied field is in the Z direction and the nucleus is placed in the magnetic field. So there will be interaction between the two, and the energy of this interaction depends on the angle between the magnetic moment and the applied field. Okay. Um, so this angle, so mu and B. Okay. So the lowest energy arrangement is when this angle is zero. So if this angle is zero, then what will happen? Then this it will have the least energy. It will have the least. It will it will have the least energy. While if they are opposite to each other, if this magnetic moment and the magnetic moment uh, is opposite to the external magnetic field, then it will have the highest energy. Okay, so the energy of interaction between the magnetic moment, which is represented by the small arrow. So this is the so this is the magnetic moment mu, and the applied magnetic field, which is denoted by this arrow V naught. It depends on the angle theta. It depends on the angle theta. So that angle theta will is so the energy between these two, energy of interaction between the magnetic moment and the externally applied magnetic field, is related to each other by the angle between these two terms, between the magnetic field and the magnetic moment. So the low, what will be the lowest energy? Lowest when this theta will be equal to zero. When the theta will be equal to zero, energy will be lowest, and when the energy of interaction will be lowest, and when theta equal to 180 degree, then what will happen? Then the energy will be maximum. Okay, energy will be maximum. Lowest energy for zero when theta equal to zero, that is what is shown in the figure. Lowest energy when theta equal to zero, and when theta equal to 180 degree, it will have the highest energy. So most of these texts and all these figures are taken from the book James Killer. James Killer is a very standard book for NMR spectroscopy, so you can go through that book as well, and all the lectures are actually sufficient. But for a better understanding, I have taken most of this thing from the book James Clear. So what you can see over this figure is again taken from that book. So you can see that all these individual magnetic moments, that they are randomly oriented. So But in presence of magnetic field, what happens that the net magnetic moment gets oriented in the z direction, and we get a overall net magnetic field vector, which is called as the bulk magnetization. So that is what is here written here. So the energy of the spins in our sample is minimized if all of the individual magnetic moments align with the field. All these are the individual magnetic moments. So all the nuclei that are present, they are randomly oriented, but so if all these magnetic moments align with the field, then we get the least energy. However, this alignment is opposed by random thermal motion of the molecules, which is trying to drive the system to state where the magnetic moments have random orientation. There are now these orientations will fluctuate because of the thermal motion of the nuclei. They will continuously fluctuate, and as a result of the disruption due to thermal motion, the individual magnetic moments are not able to adopt the lowest energy arrangement. So, what is the lowest energy arrangement? So, you would expect the uh, lowest energy arrangement if all the magnetic moments, so all these mu1, mu2, mu3, mu4, all of these are oriented in the same direction as the external magnetic field, but there are thermal fluctuations. As a result of this, all the magnetic moments are not able to orient in the same direction, or they are not able to attain the lowest energy state. Okay. So for nuclear magnetic moments, the interaction with the field is so small that across the sample, the arrangement of the moments is almost random. So their arrangement of these moments are random, right? However, there is a small preference for alignment with the field, and this, when averaged over the sample, gives rise to a bulk magnetization of the sample parallel to the field direction. So when you sum up all the different orientation of this magnetic moment, you get a net magnetic moment in the z direction. Okay, so which is parallel to the field direction. So this magnetization is represented by a vector called the bulk magnetization vector. So is this point here? So what is all in all, what it is trying to say is that the magnetic nuclei, all the nuclei will have different magnetic moments which are oriented in different directions because of the thermal fluctuation. Okay. So I hope you have understood the concept of bulk magnetization vector. That overall, if we sum up all the magnetic moments, the direction of all the magnetic moments, they are having a preference in most of them are having a preference in orienting in the same direction as the magnetic field. So it will have a net magnetization in this. Just give me a moment. Okay, so now what happens in equilibrium magnetization? So these concepts are important when we have to understand the spin lattice and spin realization. So when no field is applied, what happens? You can see here that all these magnetic moments are randomly oriented. Okay, when no field is applied. Now, when you are applying an external field, magnetic field, most of the nuclear spin will have a preference of orienting in the same direction as the externally applied magnetic field. Okay, so as a result, what happens? So at equilibrium, so when the field is applied, it will take time for the all the nuclear spins to orient in the same direction as the magnetic field. But after some time, an equilibrium will be reached where what will happen when you will add all these magnetic moments, you will get a net magnetic moment in the z direction. Okay, so that is what is shown over here. So this is again from the book James Clear. You can refer to the book. So all these figures are from that book. So on the left is shown the case when no magnetic field is applied, the individual magnetic moment are at random orientation, so that summed over the sample there is no net magnetization. Okay, so in absence of any external magnetic field, the net magnetic moment is zero. Mu is equal to zero. Okay, why is it so? Because if you add up all these, they're all randomly oriented, right? They're all randomly oriented, and if you do a vector addition of all these different magnetic moments, you will get the vector sum to be zero. Net magnetization will come out to be zero, mu net. Now, in the presence of magnetic field, there is an energetic preference for moments to be aligned with the field. So most of the moments will have a preference for aligning with the field because that is the state which is having the least energy. Okay, that energy state will have the least energy. That is why most of the magnetic moments will try to be aligned in the same direction as the magnetic field. So when the magnetic field is first applied, there is still no magnetization. However, after waiting sufficient time, the orientation with the moment parallel to the field becomes more populated. So with time, what you can see here that like if you considered one, two, three, four, five, you can see that almost five nuclear magnetic moments are oriented in the same direction as the direction of the magnetic field, and there are only three or four three three magnetic moments which are oriented in the opposite direction. So you have a net magnetic moment which is oriented in the. Just give me a moment. Okay, so your net magnetic moment, which will orient in the z direction, which is called the equilibrium magnetization. So there is a net magnetization along the direction of the field. Okay, so the process by which the spins come to equilibrium in a magnetic field is called relaxation. So that is why I try to discuss this concept. So the process. So you are applying when you are applying a magnetic field, the spins which are randomly oriented, they start to orient in a direction which is parallel to the magnetic field. So that process is called relaxation. So for nuclear spins, it is a relatively slow process. It can easily take several seconds for the equilibrium magnetization to build up. Okay. The energy of a particular magnetic moment depends on the angle between it and the applied field. So thus we saw that it will depend on the angle which is present between the external magnetic field and the magnetic moment. However, it turns out that the energy is independent of the orientation of the moment in the xy plane. So in the transverse plane, the net magnetization is zero because they are all uh, so like if you add up all the components, then it will give you a value zero. So as a result, there is no energetic preference for any particular orientation in the xy plane. So at equilibrium, we expect that the components of the individual magnetic moments will be distributed randomly. Averaged over the samples, these individual transverse components. So transverse components are those which are in the z direction, and sorry, transverse means they are oriented in the xy direction. Longitudinal components will be those that are oriented in the z direction. They'll cancel one another out such that there is no bulk magnetization in the transverse plane. Okay, in the transverse plane. So what happens is that if you break up the magnetic moment into the x component and the z component, xy component and the z component, so that is in three-dimensional space. So you will get both xy component and z component. So all these xy components will cancel out each other. So in the transverse direction, there is the net magnetization is zero. Okay, transverse direct or transverse plane. In the transverse plane, the net magnetization is zero, while in the longitudinal plane, the net magnetization will add up to give a magnetization vector, which is called the equilibrium magnetization vector, because it is the magnetization which is attained after allowing the sample or after allowing the nuclear moments to relax to that equilibrium state. Okay. So what is so Larmor precision we discussed right now? Okay. So the Larmor frequency is omega naught is equal to minus gamma b naught. So this is what I was trying to explain. So E is equal to basically is H omega naught. You can say it is minus. There is a minus term in it. So the equilibrium magnetization vector is fixed in size and direction. It does not vary over time, which is a particular property of the equilibrium state. So this vector is fixed in size and direction. But what will happen that when you will apply that external magnetic field, then this magnetization vector will get tilted. It will tilt from its z-axis. It gets tilted away from the z-axis, and the magnetization vector rotates about the field direction, sweeping out a cone of constant angle to the z-axis. This motion is called precision. So when you are applying the net, when you are applying the when you are applying the magnetic field, it gets tilted from its this equilibrium magnetization. Equilibrium, this magnetization vector is tilted from its z direction, and now it starts to precess around the z direction, sweeping out a cone of constant angle to the z axis, and this motion is called precision. And the motion is having a frequency which is called the Larmor frequency. Okay. The direction of the precision shown is for a nucleus with a positive gyromagnetic ratio and hence a negative Larmor frequency. Okay. So yeah. So positive gyromagnetic will have a negative Larmor frequency. The frequency of precision is given by nu naught equal to minus gamma b naught by 2 pi. This one, same. Nu is equal to gamma b naught by 2 pi. Okay. This precision is the Larmor frequency. Now, origin of relaxation. So the origin of relaxation is a process by which over time the bulk magnetization returns to its equilibrium position. So at equilibrium, what is happening? There is no transverse magnetization. So that is what I was explaining. So when you are applying a external magnetic field, the bulk magnetization is tilted from its axis. Now, when you give some time, what will happen? What will happen is this the transverse magnetization. The transverse magnetization at equilibrium will attain a zero value. Okay. Okay. But the longitudinal magnetization will attain a value which is called the equilibrium magnetization. This is basically called the equilibrium magnetization. Okay. So the size of the equilibrium Z magnetization depends on the number of spins, their gyromagnetic ratio, and the size of the applied field. So that is what is shown here. So relaxation drives the Z magnetization to its equilibrium value. So that is what is relaxation. It is driving the Z magnetization to its relaxation value. Yeah, so this is the relaxation value which is denoted in this figure. This is the relaxation value which is denoted by the dash line, and the transverse magnetization to its equilibrium. So the transverse magnetization will become zero at equilibrium, and the longitudinal magnetization will be attain a attain a equilibrium value, and this is called the equilibrium magnetization. So at equilibrium, all quantities cease to be time independent. That is, nothing is changing. Okay, so the moment is a vector quantity having a particular magnitude and direction. The magnitude is determined by the gyromagnetic ratio of the nucleus, right? So mu magnetic moment will be equal to what? It is equal to minus gamma p. Okay, so that will also depend on the mu is equal to gamma p, not minus, mu is equal to gamma p. So the whether the magnetic moment and the angular momentum are oriented in the same direction or different direction will actually depend on the sign of the gyromagnetic ratio. Uh, but there are no restriction on the direction in which a particular moment can point. So in general, each moment has an X, Y, and Z component. The bulk magnetization is found. So this is important. So the bulk magnetization is found by adding together the Z components of the magnetic moment from each spin. So if you add up the Z components of each spin, then you get the bulk magnetization, and the X and Y magnetization. How will you get? You will, so all of these are different, having they are oriented differently. Some are oriented in this direction, this direction. So you can break this magnetic moments into two components, right? XY component and the Z component. So if you add up all the Z components, you will get the Z magnetization. If you add up all the XY components of the magnetic moment, you will get the XY magnetization. Okay, and if you add up all the XY magnetization at equilibrium, they attain a value of zero. And if you add up all the Z components of the magnetization moments, then they will add up to a value which is called the equilibrium magnetization. Okay, so at equilibrium, the XY components of the individual spins are distributed randomly. So adding them up results in no bulk transverse magnetization. So remember this, that at equilibrium, there is no bulk transverse magnetization. However, if a transverse magnetic field oscillating at the Larmor frequency is applied, the magnetic moment will be rotated in such a way that the angle it makes to the z-axis will be altered. So now what happens is that local fields. So what happens is that because this nuclei is spinning, it will also, each of the nuclei will produce its own magnetic field, which is called the B local. Okay, so this is called the, so each of these nuclear magnetic moments will have a has its own local magnetic field. To rotate the magnetization towards the z-axis, we need a transverse magnetic field which is oscillating at or near to the Larmor frequency. So during an RF pulse, we apply such a field deliberately, but such oscillating fields also occur naturally within the sample. So we are applying an RF pulse, right? Deliberately, but other than the externally applied magnetic field, there are oscillating fields which occurs naturally within the sample. So these fields can interact with the individual magnetic moments and thus rotate them to new position in just the same way as an RF pulse. So one nuclear spin, the orientation of one nuclear spin is influenced by the orientation of the other nuclear spin. Okay, the generation of magnetic field within the sample is from other spins in the sample. So spin A experiences a local field B local due to the magnetic moment of a nearby spin B. So basically, if you have a nuclear spin here, it will also have its own magnetic field, right? It will have its own magnetic field. This also has a, because of its orientation, it has a different magnetic field. The direction of the magnetic field will be different. So the magnetic field of this will be influenced by the magnetic field of the magnetic field which is generated by a nearby nuclear spin. Okay, so and it will also depend on the be dependent on the distance between the two nuclear spins. With respect to which is along the z-axis, the local field acts like a pulse, but rather than all of the spins being affected in the same way, the effect is highly localized. The local field is different in different parts of the sample, so each spin is affected in a different way. This is in complete contrast to a pulse which affects all of the spins in the same way. So your externally applied magnetic field will affect all the spins in the same way, but the local magnetic local B local or the magnetic field which is generated by the individual spins will affect the other nuclear spins. Okay, so visualization of how the bulk Z magnetization is driven to zero by random changes in the Z component of the magnetic moment of the individual species. So here in this figure, if you just look at this figure, so what happens is that when no magnetic field is applied, all the nuclear spins are, so there are here in this figure, the example of 20 nuclear spins have been shown. Without any magnetic field, all the 20 nuclear spins are present in the lower energy state. Now, after sometime what happens that there are 3 4 nuclear spins which are moving to the higher energy state, so the now the bulk magnetization becomes minus 16, or the energy the component takes the, whereas if the spin is along the component takes value -1. Now with time what is happening, these around at in figures you can see 8 such nuclei are moving to the higher energy state, so now you are having a value of -12. Okay, now with time, what happens? There is an equilibrium state is attained where the number of nuclei in the lower energy state and higher energy state equalizes. So you have the magnetic moment zero. Okay, Z magnetization after some time will become zero. but this is not the case. So we will in the and some of the next lectures we will see that what are the other factors which control that the bulk magnetization cannot be zero. Okay, after a short time, so what this is what has all of the z components along minus z, so that the total z magnetization. So here you are basically considering the z component. Okay, so if it is here at this position, it will have a minus value. If it is moving away from this position, it will have a plus value. So you here you have 0, here you are having minus 20, here four molecules have left, you are having minus 16 z component, here you are having a z component, net z component minus 12, and you are here you are having 0. So now longitudinal, what is longitudinal relaxation or spin lattice relaxation? So what happens is that the local fields are varying on account of random thermal agitation of the molecules in the sample. So all these different spins are in thermal motion. Now, the interaction of the spins with the applied magnetic field and the thermal motion of the molecules can both be thought of as leading to reservoirs of energy. The two reservoirs can come to equilibrium as a result of mediation provided by the local fields. That is, the local field create thermal contact between the two reservoirs. So there is a thermal motion between the nuclear spin, which is giving the energy of thermal motion, and along with that there is an interaction of the magnetic moments with the externally applied magnetic field, which is giving us the magnetic energy of spins. And what is happening, we can consider that the local fields that are created, that is acting as a reservoir between the two energies, and it is trying to achieve an equilibration between the two different energies. So when the bulk magnetization is rotated away from the z-axis, the energy of the spin is increased, right? Energy of the spin, matlab this one is getting increased when you are applying an external magnetic field. This energy will increase because since those magnetic moments are aligned with the z-axis, the lower energy arrangement is decreased. Right. So when you're applying external, the lower energy arrangement, which means that most of the magnetic moment will be in the same direction as the magnetic field, that number will decrease. So you will have a low energy arrangement. The process by which jet magnetization is returned to its equilibrium value is called longitudinal relaxation or spin lattice relaxation. Okay. So this is the process. So when you are applying an external magnetic field, the equilibrium is lost, right? And the process by which this Z magnetization is returned to its equilibrium value. Okay, Z magnetization is returned. Z magnetization, or we can say that the longitudinal magnetization is returned to longitudinal, right? B magnetization, the longitudinal magnetization will return to equilibrium. That is the spin lattice relaxation. So because it is the interaction between the spin energy and the lattice energy. So this term lattice arises from the understanding that this kind of relaxation involves the flow of energy between the spins and the molecular motion. Okay, so the lattice is a generic term used to describe a reservoir of energy, which in this case is the molecular motion. So spin lattice or longitudinal relaxation processes are those that occur in the direction of the field. So your field is in the z direction. Okay, B naught. So that is the relaxation process which is taking place in the z direction or in the direction of the field is called the spin lattice or the longitudinal relaxation. Okay, the spins lose their energy by transferring it to the surroundings. So that interaction between the spin and the magnetic moment and the magnetic field is lost by transferring to the surrounding. That is why it is also known as spin lattice relaxation. As thermal energy, ultimately the lost energy heats the surrounding. So the spin lattice relaxation time is called T1. T1 is what? T1 is spin lattice relaxation. T1 relaxation, the inverse of the spin lattice relaxation or spin lattice relaxation is also called as longitudinal relaxation. Longitudinal relaxation means after you have applied an external magnetic field, the time that the nuclear moment, magnetic moments take to achieve that equilibrium magnetization, that is called the T1. Okay. Now coming to transverse relaxation. Transverse relaxation means the spin relaxation. Okay, spin relaxation is the transverse relaxation, and it is given by the term T2. Spin or transverse relaxation processes are those that occur in plane perpendicular to the direction of field. So this is your direction of the field, and if the relaxation is happening in a direction which is perpendicular to the direction of the field, then that is called the spin lattice relaxation. So what is happening when you are basically what is happening is when you are applying the external magnetic field, your components in the z direction and your components which are there in the xy direction, they both will be perturbed. So now the time that will take for the x and y components to achieve its equilibrium position, that is transverse relaxation, and the time that the z components will take to attain their equilibrium position or equilibrium magnetization, that is the T1 relaxation. So that is all. So you can go through this text, but in very simple layman's language, that is what is happening. That your XY component is getting perturbed, and the time that the XY component is taking to reach an equilibrium state of zero, that is the transverse relaxation or the spin relaxation, and the time that is taken by the Z components to achieve a equilibrium position, that is your longitudinal relaxation. Now there are several equations to analyze to understand what is this, how is this taking place, what are there are lot of quantum calculation, but we which we can see in the upcoming slides. But today let's just understand the basic concepts of these. Now chemical shift. What is a chemical shift? Is basically that just now we saw that all these nuclear spins are having a these nuclear spins are having a is producing a magnetic moment around itself. It is producing a local magnetic field. Uh, now this and also these nuclei are surrounded by electrons. They are surrounded by an electron cloud. So when you apply an external magnetic field, the electron cloud will oppose this magnetic field. So that is what is called the chemical shift. So this phenomena arises due to the fact that the electronic environment around the nucleus screens the applied magnetic field. So the electronic cloud which is surrounding that nucleus, that will screen the magnetic field that is applied. So it will not the shift will not be will also be influenced by the electron cloud which is surrounding the nuclei. So the applied field induces currents in the electron cloud which produces a magnetic field that mostly opposes the external magnetic field. Okay, so there will be currents induced. So when the magnetic field is applied, each of these nuclei will also have its own. It will induce a magnetic field in the nuclei in each of the nuclear spins as well. So as a result, which will oppose the externally applied magnetic field. So this is termed as screening by the electron cloud. And because of the asymmetry of the electron cloud around the nucleus in a given molecule which has a definite shape, the induced field will have different orientations depending on the orientation of the molecule with respect to the applied field. So H local is basically the local magnetic field, and that will be equal to the externally applied magnetic field into 1 minus a screening constant sigma local. So this we will see in the next class, that how we can get this screening constant, local screening constant. Now try to answer these questions. So we covered all these, most of these points. We will take up chemical shift in detail in the next class. So one by one, let's try to answer a few questions, solve a few questions. So the radio frequency falls in the range of the following. So you know that the electromagnetic spectrum, it ranges from the gamma rays to the, then there are gamma rays, X rays, UV rays, then visible light, then there are infrared rays, X-rays, UV rays, visible light, then you have infrared rays, then you have microwaves, and then there you have the radio waves. So radio waves are so if you consider the electromagnetic spectrum arranged in order of energy, then the radio waves are having the least energy. Okay, least energy means they will have the least frequency. Okay, and these transitions that are taking place. This nuclear spin transitions are only observed when you apply energy in the radio frequency range, which is detectable in the NMR spectra. Okay, so that is the answer for this question is actually 10 to the power 6 to 10 to the power 10. So you can have an idea of the frequencies of the different electromagnetic radiations. Okay, so you can see here that this radio frequency waves are having the least energy. least energy, so they will have the accordingly they will have the least frequencies, 10 to the power 6 to 10 to the power 10. So the least frequency is that of option 1. So answer is option 1. So which of the following set of nuclei has all non-zero magnetic moment? So we just now saw that magnetic moment is directly proportional to the spin quantum number or the spin angular momentum. Mu is directly proportional to P, mu equal to gamma P. So if and P is what? What is P? P is equal to h bar root over I into I plus 1. So what will happen? So if your I is equal to 0, I is equal to 0, then your P will be 0. And if your P is 0, then mu will be 0. Okay. So is this clear? So now coming to each of the nuclei. So H1 is having an I of 1, half. H is having a proton has a spin quantum number 1, O17. So just look at the, you do not have to, even for this question, you do not need to memorize the spin quantum numbers. So if you just look at the mass number, then only you can comment on which nuclei will have a zero spin quantum number. So O17, it is a odd number, right? Odd atomic mass number. So so it will not have I equal to 0. Right, it will have some integer value. 15n is also having odd number, but S32 is even number, so it will have I equal to 0. So in this case, S32 will be I equal to 0. So you're now moving to the second option. This 2 H2, but the atomic number is 1. So this is having a spin quantum number of 1. So this is NMR active, or this mu is not 0. F19, if we see, it is having a spin quantum number half. C13 is having spin quantum number half, but O168 is having a spin quantum number 0. Now you want an option where all the nuclei will have I not equal to 0, basically. I not equal to 0 or mu not equal to 0. So here in this case, B10, B5. So this is not NM, this will have some spin quantum number. Okay, it will have integer quantum spin quantum number. N14 will have the atomic number is 7. So this also, here also it will not have a zero magnetic quantum number. C12, this is 0. C12 will have 0. So this option is false. But here, if you see option number 4, here it will, here the I, here the I is half. For 1, it is a proton, it is 1. C13, I is 1. For N15, the I is 1. For sorry, half. C13 it is half, for N15 it is half, and for F19 it is half. So if they are having spin quantum number not equal to 0, then their magnetic moment will also be not equal to 0. So answer option 4 is correct. Okay. So it's the same thing that we have gone through in the lecture. Okay. So just remember this concept. Scribbled a lot. Just rub it. So just remember this concept that if I is not equal to 0, then what will happen? Then your P will nuclear magnetic moment, angular momentum. Nuclear angular momentum will not be equal to 0. Your mu will not be equal to 0. This is the concept. So you have to look for nuclei which are having I not equal to 0. So the number of orientations possible for the nucleus with spin I equal to 3 by 2 will be given by 2I plus 1. Okay. So it will be 2 into 3 by 2 plus 1, which will be equal to 4. So it will have minus 3 by 2, minus half, half, and 3 by 2. These are the possible orientation. Answer is 4. Okay. So 29 SI has I equal to 3 by 2. Its magnetic quantum numbers are what? So it will have this minus 3 by 2, minus half, plus half, and 3 by 2. Answer is option 4. Okay. With increments of 1. So remember, M takes values of from minus I to plus I with increments of plus 1. So you do minus 3 by 2, then again you add minus plus 1 to this, then you again minus 3 by 2 plus 1, then you do minus 3 by 2 plus 1 plus 1 plus 1 till you get the ith value, minus I to I value. A proton in a magnetic field of 17.1 Tesla is equal to what? So one thing here you have to remember is that you have to remember a conversion factor of Tesla and megahertz. What is the relation between Tesla and megahertz? So nu is equal to gamma b naught, right? Gamma B naught. So just remember that this gamma is equal to 42.577 megahertz per Tesla. So you are now given that the field is 17.1. So you multiply 17.1 and then you will have the frequency of 750 megahertz. Okay, we have seen this here, right? Gamma by 2 pi into B naught. So I hope this question is clear. So you remember that nu is equal to 42.57 megahertz per Tesla. So if whatever Tesla you have, you multiply it by this factor, you will get the frequency. Okay, so that will be 750 megahertz. So which of the following is the correct order of sensitivity? Now sensitivity of a nuclei is dependent on three factors. One is the abundance. Abundance, it will depend on the abundance, it will depend on the gyromagnetic ratio, and it will also depend on the, it will also depend on what? The magnetic moment as well. Yeah, magnetic moment. So these are the three factors: magnetic moment, spin quantum number, and the gyromagnetic ratio. So what you can see here, if you compare all these, is proportional to gyromagnetic ratio and natural abundance. So the one which is having a higher gyromagnetic ratio and higher natural abundance will have a higher sensitivity. So out of all these, you can see that P31, like proton is having a very high percentage abundance, right? And it is also having a very high gyromagnetic ratio. So proton has the highest sensitivity, followed by P31. P31 has a lower gyromagnetic ratio compared to proton, but it is having a very high natural abundance, 100%. That is why then it will be P13. C13, the gyromagnetic ratio of nitrogen is negative. So there is only so you have to remember that N15 has a gyromagnetic ratio of negative. So obviously the sensitivity of 15N will be the lowest. Okay, so there is only one option with where 15N is having the lowest sensitivity. So that is the option one is correct. Okay, now if a proton absorbs at a frequency of 750 megahertz, then carbon will absorb at a frequency of approximately. So as I was discussing that the gyromagnetic ratio of carbon is almost four times the gyromagnetic ratio of hydrogen. Okay, so if you are if your proton is absorbing at 750 megahertz, then you just divide it by 4. Okay, so if you divide it by 4, then what will you get? You will get this value around. So you will get option 1 is the correct answer. Okay. So answer is option 1. So NMR spectroscopy is least sensitive technique because what? Because of the small difference between the alpha and beta states. Alpha and beta spin states are the lower energy state and the higher energy state. The lower energy state is alpha, higher energy state is beta. So that is given by the Boltzmann statistics n beta by n alpha e to the power minus delta e by ekt. Okay. Now the Larmor precision frequency of C13 in a magnetic field of 9.4 Tesla is 100 megahertz. If the magnetic field is increased to 18.8 Tesla, what is the frequency basically? Okay. So what we learned is that Larmor frequency is what? It is gamma V naught in a way. Okay. Gamma V naught. So you just divide it. So you know that the so you just new or C13 divided by new H1. Okay. You have C13. You know if you know the value of gyromagnetic ratio of C13. And you know the magnetic field that is used for the carbon 13 is what? It is 100 megahertz. You want to determine the magnetic field to, you have increased it to 18.8 Tesla. Sorry. This you want to determine V naught. V naught for C13 you don't know, but you know the V naught for hydro proton, which is 18.8. Now, what all information you have? That you know this is 100 megahertz. Okay, this is 100 megahertz. You don't know the value of this. What will be the frequency, Larmor precision frequency of proton? You don't know the Larmor precision frequency of proton. So you substitute it by the value x, and you know that C13 is 1 by 4 that of proton. So you put it over here. Well, this will be 1 by 4. You do not uh, so this is actually, it is increased to 18.8. Okay, so from here you can calculate the get the value of x. Okay, so just go through this. So yeah, 9.4, 9.4. Okay, so you put here 9.4 and you will get the value. Okay, so you know this is 100. This is 100, but you have put it over x over here. This will be 1 by 4. This will be 9.4, and this will be 18.8. Now you substitute x, you will get 800 megahertz. Okay. For spin 1 nuclei, the direction of orientation of the spin angular momentum with respect to the magnetic field. So if you are having spin angular moment, spin quantum number 1, then it will have what values? It can take two values, plus half and minus half. Is it? Or it will have minus half, minus I to plus y, plus I. Okay, so it will have -1 and +1 values. The direction of the orientation of the spin angular momentum will respect to. So basically, you have your spin quantum number 1. Okay, so in this case, what will be the spin states? It will have 2i plus 1 values. It will have three values. So what will be those three values? It will be -1, -1 plus 1 will be 0, then 0 plus 1 will be 1. So it will have three values: 0, this will be 1, this will be -1. And now you can actually calculate this theta angle. So you have been asked to calculate the theta angle. So you can plot it from, you can get it from here actually. So these type of things have been discussed in the lectures already. So this will be 0, this will be 1, this will be -1. And you know that the quantum angular momentum, angular quantum, spin quantum angular momentum will be h bar root over I into I plus 1. So it will be h bar root over 1 into 1 plus 1 is 2. So here you will have h bar root 2, and this will have a value of minus h bar root 2. So if you want to calculate this value theta, then what will be cos theta? Cos theta is base by hypotenuse, right? So this is the base. Base is what? Base is having the value. Your hypotenuse is having a value h bar root 2. Okay, and base is having a value 1. So basically, y is 45 by 2 by root over I plus 1. So if you are having a spin quantum number 1, then it will be root 2 h by 2 pi. And pz will be what? Pz will be 1 into h by 2 pi. Pz, this is pz, and this is your p value. Okay, so cos theta is basically what? Cos theta is equal to pz by p. So your pz is 1, is h by 2 pi, and your p is what? P is root 2 h by 2 pi. So this will get cancelled, and cos theta will be 1 by root 2. Cos theta will be 1 by root 2. So their theta will be 45 degree, and minus this will be 45 degree. This will be minus 45 degree. Okay. More the shielding effect, what will happen? So we will discuss this concept in the next class. But if the shielding effect is more, then the chemical shift will be lower. Okay, because it has an induced magnetic field which will oppose the applied magnetic field, and then therefore the chemical shift. this chemical shift that you see, we will see that this is denoted in ppm, and here you have the absorbance. Okay, so because it is having a local magnetic field, the external applied magnetic field will be screened. The local magnetic field will screen the externally applied magnetic field, and more the shielding will be there, there will be less chemical shift. Okay, the chemical shift will be less. Answer is option A. In an NMR experiment, the radio frequency, so the radio frequency is always oriented 90-degree to the main field. So if your field is in the Z direction magnetic field, your radio frequency is always 90-degree, is applied at an angle 90-degree to the externally applied magnetic field. Okay. Option B. T1 relaxation, we just now learned that T1 relaxation is what? T1 relaxation is spin lattice relaxation. Spin lattice relaxation, isn't it? This spin lattice relaxation. Or relaxation in the longitudinal axis. Longitudinal relaxation. Spin lattice relaxation means longitudinal relaxation. What does RF do in an NMR experiment? So what happens when you apply radio frequency? It will so there will be upward and downward transition of spins with equal probability, isn't it? So this thing has been very well explained by Professor Hosur in his in the lectures. So there will be upward and down. There is equal probability of transition to the upward energy state and the higher lower energy state. Okay, answer is option B. Now this is one of the question which we will understand more in the next class. But for now, what you have to understand here is that the frequency range of, so here in this question you have been asked to calculate to comment on the frequency range of chemical shifts of proton in a 500 megahertz spectrometer. So the thing is that the frequency range is, so if you see for a proton spectra, this proton spectra ranges from 1 ppm to 12 ppm. Okay, 1 ppm to 12 ppm. And the one thing is that the frequency is always equal to the ppm, whatever ppm is there, into the reference frequency. So if your reference frequency is 500 megahertz, then it will be 500 uh, uh, hertz. 500 hertz will be the frequency. Okay, but here you can see that it ranges from 1 ppm to almost 12 ppm. So you can put here 12. Okay, 12, or you can put here 10. So if you multiply 12 with 500, then what you will get? You will get around 6 kilohertz. You will get around 6 kilohertz. So answer is actually option C, 5 to 10 kilohertz. We will look at the conversion of ppm megahertz to ppm in the next class. But for understanding this question, just have to understand this point, that 1 ppm is always equal to the reference frequency. It is not 1 ppm is not is would correspond to, if it is a 500 megahertz spectrometer, then 1 ppm would be 500 hertz. If it is a 800 megahertz spectrometer, then 1 ppm would be equal to 800 hertz. So since it is a 500 megahertz spectrometer, then therefore 1 ppm is corresponding to 500 hertz. Why is this so? We will understand in the next lecture in detail. But 1 ppm is always equal to the reference frequency of the reference spectrometer. Okay. So that is why you can see that proton NMR spans from 0 ppm to 10 ppm. So that is why 10 ppm would be what? It would be 500 into 10. So 500 into 10 is 5 kilohertz. But if it extends from 0 to 12 ppm, so you can, if you have multiplied 12 with 500, then you will get 6 kilohertz. So that is why the answer is option C. So that was all for today. I hope you will go. So most of many of you couldn't join today's session, but I will upload the lecture and you can go through the lecture. And if there are any doubts, we can take it up in the next class. So thank you all.